In this series, we will look at the decision tree algorithm. Let's look at how to use decision trees to perform classification and regression. This video was produced in Korean and then translated into English. The voice was generated using text-to-speech. Let's take a look at the full table of contents of the decision trees. In Chapter 1, we will look at an overview of decision trees. Let's briefly look at the types and history of decision trees, and then look at an overview of the ID3 and CART algorithms. We'll then compare the differences between trees generated by ID3 and CART algorithms. Next, we will look at the concept of split points used when constructing a tree, and how to predict the target class of test data using majority voting. In Chapter 2 and 3, we will look at the ID3 and C4.5 algorithms. In Chapter 2, we will look at classification model, and in Chapter 3, we will look at regression model. In Chapters 4 and 5, we will take a closer look at the CART algorithm. In Chapter 4, we'll look at classification algorithm, and in Chapter 5, we'll look at regression algorithm. Since CART is more widely used than ID3, let's take a closer look at CART. Let's take a closer look at the CART algorithm and see how it finds the best split point. We'll also write code from scratch to construct a decision tree using recursive tree splitting. Now, let's briefly look at the history of decision trees. Before the 1980s, the first-generation tree algorithms were proposed. In 1963, the AID algorithm was proposed. In 1972, the TIDE algorithm was proposed, and in 1980, the CHAID algorithm was proposed. AID is the first regression tree algorithm, and TIDE is the first classification tree algorithm. CHAID is a tree algorithm that extends the earlier AID and TIDE and performs both classification and regression. In the 1980s, algorithms such as CART, ID3, and C4.5 were proposed, which are called second-generation tree algorithms. CART is a tree algorithm proposed by Leo Breiman in 1984. And ID3 is a tree algorithm proposed by Ross Quinlan in 1979 and 1986. C4.5 is an extension of Quinlan's earlier ID3 algorithm. Since then, until the 2000s, algorithms such as Quest, Cruise, and Bayesian CART have been proposed, which are called third-generation tree algorithms. And since the 2000s, various tree algorithms such as Guide, C-tree, and Mob have been proposed, which are called fourth-generation tree algorithms. In this series, we will take a closer look at the ID3, C4.5, and CART algorithms, which were proposed in the 1980s. For more details on this, please refer to this document. Next, let's briefly look at the history of ID3, C4.5, and CART. ID3 is an algorithm proposed by Ross Quinlan in this paper in 1986. ID3 stands for Iterative Dichotomizer 3. In 1993, Ross Quinlan proposed the C4.5 algorithm, which extended his earlier ID3 by adding several features. Additional features include the ability to handle missing values and perform pruning. And CART is an algorithm called classification and regression trees, proposed by Leo Breiman in this book in 1984. CART decision tree is more widely used than ID3. It is widely used as a base model for ensemble learning, especially random forest GBM, XGBoost, and light GBM. So let's take a closer look at the CART algorithm rather than the ID3. Next, let's compare the features of trees generated with ID3 and CART. First, let's look at the dataset we'll be using. On the left is the training dataset, and on the right is a single test data point. This dataset has 3 features and 1 target class. The feature's favorite color and sex are nominal variables, and the feature age is a continuous numerical variable. The target class consists of 0 and 1. This is part of the Titanic dataset. I've added a favorite color feature here for testing purposes. Let's use this dataset to create an ID3 decision tree. First, we split the root node using the favorite color feature. The favorite color feature consists of 3 categories: red, blue, and green. ID3 creates multi-way splits like this, depending on the number of possible values for a given feature. Next, we split the child nodes using the sex feature. The sex feature has 2 possible values, male or female. Let's find the data points in the training dataset where the favorite color is red and the sex is male. Here is one, and here is another. Here are 2 more, and here's the last one. Target class 1 means survived, and 0 means not survived. Data points with a target value of 1 are shown in blue, and data points with a target value of 0 are shown in red. These 5 data points we found then belong to the first leaf node of this tree. In this way, every data point is assigned to the leaf node to which it belongs. Next, let's use this dataset to create a CART decision tree. The CART algorithm constructs a binary decision tree. Each node is split into 2 child nodes based on yes or no. First, let's split the root node using the age feature. Any data points with a feature age value less than or equal to 33 are assigned to the left node, and any data points with feature age value greater than 33 are assigned to the right node. Next, we split the child nodes using the sex feature. For the sex feature, male is defined as 0 and female as 1. If the sex is less than 0.5, it is male. Otherwise, it is female. Let's find the data points in the training dataset where the age is less than or equal 33 and the sex is female. Here is one. And here is another. These 2 data points belong to this leaf node. all are red. In this way, every data point is assigned to the leaf node to which it belongs. Next, let's use these trees to predict the target class of the test data. The favorite color is red, and the sex is male. This test data point will belong to this node in the ID3 decision tree. Then the class of this test data point is predicted as blue, won by majority vote. Next, let's use this CART decision tree to predict the target class. Since age is 13, we go to the left child node, and since sex is male, we go to the left child node again. Then, this test data point belongs to the first leaf node. Since this node contains 3 reds and 3 blues, we can assume that this test data point is blue with a probability of 50%. This is how a decision tree works. It asks questions about the data and follows the branches until it gets to an answer. Let's consider a few issues here. In this example, we did not use the age feature for ID3 because multi-way splits is not suitable for features with continuous real values. To do this, we need to convert the continuous real values into categorical values. We can see that while ID3 is powerful in handling categorical features, it may not be suitable for handling continuous features. Also, although we use the favorite color feature as the first split condition, we could have used the sex feature first. We need to consider which feature is the best to split on at each node. Next, let's look at the problems with CART decision trees. In this example, we did not use the favorite color feature in the CART decision tree. Because this is a nominal feature with 3 categories, it cannot be split into 2 child nodes in this way. To do this, we need to one-hot encode this feature, or split it into 2 subsets, such as red versus others, blue versus others, green versus others. Additionally, the numbers 33.5 and 37.5 were used as splitting points here. But we need to know how to find these numbers. We will discuss these issues in more detail one by one later. Next, let's look at how to construct a CART decision tree, the concept of split points, and majority voting through another example. This time, we will be using this data set. The training and test data sets are as follows. This dataset has 2 features, x1 and x2. The target class y consists of 0 and 1. Let's plot each data point as a single point in a 2-dimensional space consisting of the x1 and x2 axes. Data points where the target class y is 0 are shown in red, and data points where it is 1 are shown in blue. Let's consider 4 split points in this space, A, B, C, and A'. The split points A, B, and C lie on the x1 axis, and the A' lies on the x2 axis. Let's use these split points to create a CART decision tree like the one on the right. First, we split the feature x1 using the split point A. Data points where the x1 feature is less than or equal to A. are assigned to the left node. This node contains 8 reds and 1 blue. And the data points where the X1 feature is greater than A are assigned to the right node. Next, we split the feature X2 using the split point A'. Data points where the X1 feature is greater than A and the X2 feature is less than or equal to A'. Are assigned to the left node. Data points where the X1 feature is greater than A and the X2 feature is also greater than A' are assigned to the right node. Finally, we split the X1 feature again using split points C and B as follows. This will generate a simple decision tree for this dataset. Now that we have a decision tree, we can predict the target class for test data. In this space, the test data point A is located here. Since the feature X1 of this data point is greater than A, it is assigned to the right child node of the root node. Since the feature X2 is greater than A', it is assigned to the right child node of this node. Finally, since the feature X1 is greater than B, it is assigned to the right child node of this node. That is, the test data point A belongs to the last leaf node. Since this node contains 2 reds and 5 blues, we can assume that by majority vote, this test data point is blue with a probability of 5/7. That is, the target class of test data point A is predicted as 1. This is how a decision tree works. And our goal is to use this tree to predict the class Y of the test data. In this example, we used 4 given split points. But in reality, we need to find the best split point among many candidate split points. We will look at this in more detail later. In this video, we briefly looked at the history and overview of decision trees. In the next video, we will take a closer look at the classification model of the ID3 C4.5 decision tree.